Well, for those of you who do not know, I have a YouTube channel called Electronics for the Inquisitive Experimenter. And I'm kind of doing double duty here. They're recording this presentation, and I'm going to take that recording and edit it, and it will become one of my videos on my YouTube channel. But tonight we're going to be talking about antenna analyzers. I don't see my beautiful slide up here. There we go. There we go. Okay. We're going to be talking about antenna analyzers. And, you know, in the past, we remember in the past how it was. All we had essentially was an SWR meter, and some hams had a grid dip meter. Now, in the hands of really smart people who knew how to use these things properly, they did some pretty incredible things with these devices. But that's essentially all we had as hams to tune antennas and traps and the like. And so here you can see some of the various older and newer of those particular devices. But, you know, with the advent of the microprocessor and the microcontrollers and analog to digital converters and all that kind of good stuff and micro circuitry and all that, in marches the antenna analyzer, and all the hams applaud. Now, the original ones were pretty expensive, if you remember. They were pretty pricey, so even then not a lot of hams had them. But one of the big advantages of these is that you could set up and test an antenna, like this beautiful antenna here. This antenna, I built it in late 1990s, and this is the antenna that I spoke with Mir Space Station on. It's an SO239 and some house wiring. That's it. But it allows us to go on and using low power, test our antennas, tune our antennas, get good ideas of things, and it does a whole lot more than that. But even more recently has come in what are called VNAs, or Vector Network Analyzers. Now, what the real difference between a Vector Network Analyzer and an antenna analyzer is that a Vector Network Analyzer adds a second port. It's a matched receiver port. So the TX or the DUT or the S11 port is essentially the same thing as your antenna analyzer. It's the other port that allows you to test for insertion loss and gain of amplifiers and things like that. So tonight what I'd like to do is talk about these antenna analyzers, because a lot of the things that they do are really cool and they really help us a lot. And here are the basic kinds of measurements that we're going to be interested in. We have the SWR, we have impedance measurements, we have coax loss, we have distance to fault, and we have coax velocity factor. Now, each of these is done so differently from one antenna analyzer to the next. There's no way I'm going to give you instructions on how to do it with every antenna analyzer. What I do have here is an MFJ-259C, and I'm going to be using that as part of my demonstrations. Now, as it goes, you know, if I can only buy the stuff that's on my shopping list, I'll actually get through the whole list here tonight. So what I'm going to ask you to do is hold your questions right for the end, so I can just kind of blast through. Because, you know, this is a lot of stuff to talk about, because I not only want to tell you how to do it, but I also want to give you an idea of how it does it. A little bit of the technical stuff behind it. You know me. I have to make your eyes glaze over somehow. All right. So, SWR, also known as voltage standard wave ratio. Why on earth do we do it? Well, to begin with, we do it to tell how well matched your antenna is on a particular frequency. If your antenna isn't matched well, you're going to be expending all kinds of power and heat and not actually using it to talk to anybody. You can also use a loop pickup, like this little loop here. You hook that up to a connector, you plug that into your antenna analyzer, and you can use that for tuning traps. You just tune your antenna analyzer and you'll actually see the SWR dip. And that's where the tuned circuit is sucking energy out of the loop and causing the return to be less. So you can use it for tuning antenna traps and the like. So, how do you do it? Well, it's really simple. They've dumbed these things down so far that you can do it in your sleep practically. First of all, you put it in SWR mode. Now, this particular meter defaults to SWR mode. So you turn it on and there it is. And you can see it says SWR. Now, if I turn it off and turn it back on, you'll see they don't actually call it SWR mode. They call it, come on, they don't, let me come back around to it so you can see their impedance R and X, real and imaginary. So you got the real and you got the reactive components here, but then here's the SWR meter and so on. So you get your analyzer into SWR mode by whatever means. You determine the frequency that you're interested in. And so I'm going to say, well, this is a 2-meter antenna here, this lovely, highly technical 2-meter antenna. So I'm going to say I want to see what the SWR is right in the middle of the band. So I'm going to set the frequency for 146 megahertz-ish. All right, so I got the frequency set right. I set it on the analyzer, and now I'm going to connect up my antenna. And now you'll see that at 146 megahertz, this has a beautiful 1 point. If I'm standing away from it, it gets better when I get close. It likes me. Okay, you'll see that it's right around 1.3 to 1 in the middle of the band for a piece of wire and an SO239. Not too shabby. So there, I've read my SWR.
What's your coax factor there?
So, you just read the SWR after the antenna is on. Now, the question is my antenna too short or too long? You're tuning your antenna, you want to know what you got to do with it, right? Somehow you got to change your antenna if it isn't the way you want it. But before I do that, I want to show you something. You see that this says 1.2, 1.3 to 1, right? You've heard coax doesn't make a difference. Well, yes and no. It does not change the SWR of your antenna. It will change the perception of your SWR in the shack. I have here a roll of very lossy coax. I know it's very lossy because I've measured it. Now, if I take this, now remember what you saw, 1.3 to 1, right? And all I'm going to do is put this roll of very lossy coax in line with it. All right, it's making a liar out of me. Did I change the frequency? Not that much. I don't know why it's doing what it's doing. It should actually be indicating a lower SWR. And when I did this at home, it did. It went from 1.5 to 1 to 1.1 to 1, putting in a roll of lossy coax. So it makes a difference, but this SWR hasn't changed. I guess I'm using a different adapter here, and that's the problem. So that's just a word to the wise. The closer you can get to the antenna to make your SWR measurement, the better off you are, because then you won't have the effects of losses in your connectors, in your adapters, in your cable. You won't have that causing weirdnesses to occur in your measurements. So, is my antenna too long or too short? How are we going to discover that? Well, this is what I call a non-scanning antenna analyzer. It's non-scanning because the only scanning you get is when you take your finger and turn the knob. Okay? The scanning type are more like the rig experts and things like that, that you set the extents and you say, okay, scan it from here to there, and it scans through and takes all your measurements and puts it up on a pretty little display for you. But this is non-scanning. So how do you do it? Well, you grabbed it up. That's part of the problem. It's going to sleep. Wake up. There we go. You grab your frequency and you start going down in frequency and watch the SWR. You notice that the SWR is going up. As I go up in frequency, the SWR is going down. So in this particular case, because the SWR is going up when I go down, up when I go down and down when I go up, this is too short if I wanted at the lower end of the band. I'd have to get my cable stretcher out if I wanted to tune better. Otherwise, you'd have to snip it to get it to tune if it's too long, obviously. Now with the scanning type, you just look at the little blippy on the screen, and if the dip in the SWR happens to be below the frequency you want, well then it's too long, and if it happens to be above, then it's too short. Pretty straightforward. So, the question is, how do they do that? Well, I'm not going to get into the hot and heavy explanation of how they do that because, well, frankly, no one's really completely tipping their hand out there. I looked and looked and looked. But suffice it to say, what they have is a bridge. And these are two of the different kinds of bridges that I use. The one on the top is more like they use with the MFJ. And so they have three of the legs being 50 ohm loads, which are non-inductive 50 ohm loads. And the fourth leg is your antenna. And then they have, they pick off and rectify and create a DC voltage at those particular spots that you see. And then based on those DC voltages represent the hypotenuse of a right triangle. As you can see in the lower part here, you see the VN and the VL and so on. That's the hypotenuse of a right triangle, and the legs are representative of the real and imaginary parts that represent that voltage. Okay? That's as deep as I'm going to get into it. We'll just say that they do some trigonometry, they do some math, and they figure it out using those vectors. And then with SWR, they know the forward voltage, and they know the reflected voltage, and this is a simple little equation that they use. It's just the forward voltage plus the reflected voltage divided by the forward voltage minus the reflected voltage. Pretty straightforward, very simple equation, and they get it off of this bridge that they have. Now, we've talked about the SWR, how they do SWR, how to do SWR. Now let's talk about impedance, because you do want to know impedances. Remember, impedance is this hypotenuse of the right triangle. It's kind of like AC resistance, and this is a review for most of you, I'm sure. Impedance is kind of like AC resistance. It is the hypotenuse of a right triangle that's defined by two legs. The one leg is the resistive or purely resistive part. It's the ideal of an ideal resistor. It is not frequency dependent. It's always the same. And then there is the imaginary part, or the reactive part, which is frequency dependent. It's like an ideal capacitor and an ideal inductor. Now, capacitors have negative reactance, inductors have positive reactance. And when the positive reactance of the inductor equals the negative reactance of the capacitor, you have resonance. They cancel each other out, and the only thing you have left is the real part, the non-reactive part. So, impedance, the non-scanning analyzers have no clue about the sign of the reactive part. If you happen to notice here on here, I'm going to put this to a place where we get a reactive part. You notice that it just says X. It doesn't say X sub C. It doesn't say X sub L. It doesn't say minus 20. There's nothing you can do to make that say minus 20 because it doesn't have a clue what the sign is. But yet that does make a difference as to whether it's a capacitor or an inductor. So what do? Well, let me change out my antenna here. I have a 330 picofarad capacitor here. It's a little tiny thing. And if you look at the X number here, you notice that as I go down in frequency, what does I got to go on lower frequency here. What does the X do? The X goes up when I go down, right? If the X goes up when I go down in frequency, it's a capacitor. If the X goes up when I go down, up when I go up in frequency, it's an inductor. So that's how you tell whether this X is for capacitive reactance or inductive reactance by whether it gets smaller or larger as you change frequency. So if X goes down, as you go down in frequency, then it is inductive. If X goes up when you go down in frequency, then it is capacitive. Now I'm going to show you something interesting. This is a capacitor, right? So you would think that no matter what I did with frequency, that would always be a capacitor. Well, let's see. Look, X is 2. I'm going to go up in frequency. You notice that it's going down? Right about there, it's 0. You know what's going to happen when I go further up? All of a sudden, as I go up in frequency, it's going to start going up again. If I go up in frequency, it even goes higher and higher and higher. You know why? Because inherent in building a capacitor, they have to use wire and metal objects, which are all inductive. And what ends up happening as you go up in frequency, eventually the inductance associated with how the capacitor is built takes over, and the capacitor is irrelevant. The capacitor starts acting like an inductor. That's just a little bit of trivia. All right. So how to measure the capacitance and inductance? Some really important points here. Non-scanning analyzers will assume you are measuring capacitance if you have selected capacitance. So I go down here and I push the button, coax loss, capacitance, and picofarad. It is going to assume that I am measuring capacitance. If I stick a coil out here, and it's just a coil, it's going to look at the reactive component and say, oh, that's a capacitor, here's the value. So I can go over here and say, okay, inductance. Now that's a capacitor, but yet it's saying 0.087 microhenries. It is not measuring the inductance of the capacitor. It is just interpreting the reactive part differently. And so if you stick an inductor on there and go into this mode, it assumes that you're measuring inductor. And so it's going to look at whatever the X value is, whatever this X value is here, it's going to put it in these equations and come up with a value based on that X value. So you have to know what it is ahead of time by looking at what the X value is doing as you go up and down in frequency. You got to be mindful of the frequency you're testing at to get an accurate reading. So with that, we'll go on to coax loss. Told you I got a lot of things in my shopping basket here tonight. Coax loss. Why do you care about coax loss? Well, the big question is how good is your coax? Here I have this piece of coax here that I very carefully measured. It's not that old. It's actually about 20 years old. But on the 2 meter band, it has 4.4 dB of attenuation on the 2 meter band. I have a piece of coax at home that is 50 years old and has 1.7 dB, and it's about the same length. Is this coax worth using for a 2 meter antenna? Well, if you didn't know what its loss was, you'd probably say it's fine. I mean, you feel this coax. It's supple. It's nice. It's very aesthetic. I mean, really. I mean, look how flexible it is. But as far as 2 meters and 440, on 440, if I had a 50-watt transmitter on one end of this coax and the other end connected to a perfectly matched antenna at the other end, I'd only be getting on the order of about 11.6 watts to my antenna. Not going to use that on 440. So you take your coax, you find out what it is, you go out and look that up on the data table for the coax. Now notice that they have nominal attenuation at specific frequencies. So when you're testing your coax with your antenna analyzer, set your antenna analyzer to one of the frequencies listed. That way, when you test your coax, you can say, well, my coax has so much attenuation per 100 feet, and the data sheet says it should have this, well, then it's good, or it's bad. But that's what you do. And usually 100 megahertz is one of the numbers on the list, and they always put it in dB per 100 feet. The other question that you can answer is, well, is the coax good enough for what I want to do? Maybe it isn't great coax, but it's good enough. Well, the only way to find out is to measure its loss. Well, just like before, they make it real easy. First of all, you want to know how long your cable is. This is 9 foot 7 inches long, measured. Okay? Then you take your antenna analyzer and you set it to coax loss. You set it to the particular frequency from the data sheet. I'm going to use 100 megahertz because that's one of those magic numbers that they like. Okay? Connect an unterminated. Unterminated. And you'll understand why that's the case when I tell you how it works. Connect your unterminated coax to the antenna analyzer, and then simply read the coax loss in dB. This is 0.3 dB in 9 feet 7 inches. But my data sheet has it in dB per 100 foot, so I have to translate that to something, and I use this lovely equation here. You take the loss that you measured, 0.3 dB, you divide it by the length of the cable, which is 9.58 feet in this case, and you multiply it by 100. And then you take that number and you look at your data sheet and say, is my coax any good? So, I will tell you one other thing. If you have a 2-port VNA, like a mini VNA Tiny or a nano VNA, I would tell you I would prefer to measure coax loss by taking that and using that to measure insertion loss using your 2-port VNA. It'll give you more accurate results, more predictable. So how do they do it? Well, let's just step through it. If we had perfect coax and a perfect load, the signal or the antenna analyzer would put its power out. 100% of its power ends up at the perfect load. 100% of its power is consumed in the perfect load, and 0 reflected signal coming back, right? Now, what if we have a perfectly horrible load, but we still have perfect coax? Then the analyzer puts out power, 100% of that signal gets out to the perfectly horrible load. The perfectly horrible load then reflects back 100% of that power back at the antenna analyzer. And because we have perfect coax, we see the 100% of the power back at the antenna analyzer. Reflected power equals forward power, but we don't have perfect coax. We have coax that has loss. So that the antenna analyzer puts out its signal. It's attenuated all the way to the other end, so now less is coming out the end than what went in. Because we have a perfectly horrible load, we have an unterminated coax. Because we have a perfectly horrible load, 100% of that power that's being delivered to the end of the cable is being reflected back. But guess what? Our coax is attenuating that by the same amount on the way back as it did on the way back. So in the end, the reflected signal is significantly lower than it would have been. That's how it works. Oops, went too fast. So the power reflected is less than the power forward. The power lost is the power forward minus the reflected power divided by 2, because that difference is going to be showing loss in 2 directions, so they divide it by 2 so that and then they change that around over to dB, and they report it in dB. So that's how they do that. Distance to fault. Why on earth do you want to know distance to fault? Well, what if you have a problem with a piece of coax? You got this infinite SWR and you have no clue why. It's connected to a good antenna, it's connected to, everything is connected right, but I have this infinite SWR. What's going on? Well, this allows you to connect up your antenna analyzer to your coax and figure out where the problem is. Or maybe you have a long piece of coax like this, and I say, well, I have no idea how long that roll of coax is. I could unroll the coax, get out my tape measure, and sit there and measure it, or I can use distance default to get a rough idea of how long that is. So, what do you need to know to use distance default? You need to know the velocity factor of your coax. A lot of coaxes are 0.66 if they're made out of polypropylene, but don't bet on it because there are those that are 0.87. So it makes a difference. You need to know the velocity factor of your coax, which can be gleaned from the data sheet. As you see here, this particular type of RG58U has a velocity propagation of 66. Now, a fault is defined as a short or an open. So if your coax has been cut or something has crushed it to the point where the inner and outer conductors have made contact with one another, that's a fault. Okay, so how do you do it? Well, we set the analyzer to distance default mode. In the case of this one here, you have to go in the advanced menu. You hold down both at the same time, and then you go mode, distance default. So you get in distance default mode. Some analyzers at this point will ask you for the velocity factor. Some won't. Some will wait till the end. This one never asks you. Okay? We set the analyzer to the highest reasonable frequency for the coax that you're testing. The higher the frequency, the better the resolution you get. So I'm going to take this, I'm going to turn it all the way up. I'm up to 230 megahertz. I take this coax, this unterminated coax, and I connect it to my antenna analyzer. And now, I'm ready to start. I slowly tune down. Watch the X number. I slowly tune down in frequency. I'm going up instead of down. Notice it's starting to go down. When it reaches 0, that's the magic number. 0. Notice it says 185. I'm going to go a little bit further. And it goes up. There, it just popped up again. 182, 185, 182, right about 183 megahertz, right? And I press gate. Okay, I press gate. There we go. Now, I continue to tune down to the next point where X equals 0. Notice that it's going up. I'm going down in frequency. It's going up. It goes crazy. Now, look, notice it's coming down again. Oh, I can't quite get down there. Right. 170, 168. Oh, don't you love it? And you go down until it's 0 again. And it says 15 foot times the velocity factor. When I did this at home, it came out to 14.8 feet because I was a little more careful at home about how I did it. And you say, well, wait, this is 9 foot times the velocity factor. See, times velocity factor. That's why you need to know it. So you take the number that they give you here, you multiply it by the velocity factor. I guessed that this was a 0.66 velocity factor, and I got a a distance of 9 foot 9.2 inches. So I was within 2 inches of the real physical length. Distance to fault. So now I know the length of my cable, or you can find out, okay, now I measure out my cable, and right there is where someone stuck a shovel through my buried coax. So, how does it do that? Let's answer that real quick. How on earth do they do that? Well, first of all, distance to fault assumes a perfect fault, a dead open or a dead short. Wide open, dead short. What it does is it looks for two adjacent 1/4 wave resonant points. That's why you get the two different points. Now we know that we arrive at a quarter wave resonant point when the X number goes to 0. When the reactance drops to 0, you're at a quarter wave resonant point. Once they know these two frequencies, and it's an odd number of quarter wavelengths, by the way, that's an important point. So those two frequencies are actually a half a wavelength apart, as is evidenced by our equation here. The frequency at which this is 1/4 wavelength long is found by the difference between the two frequencies that I got on here, divided by 2. Once they have that frequency, that F0, they can quickly calculate the length, the electrical length in feet. That's that 14.8 feet is the electrical length, by dividing the speed of light in feet per second by the frequency in hertz. Done, you got the electrical length. But notice the electrical length is longer. Well, that's because of the speed of propagation. So if you take the electrical length and you multiply it by the velocity factor, you get the physical length of the cable. Pretty cool, huh? Last but not least, velocity factor. Why on earth do you want to know velocity factor? Well, you want to find out if your coax is any good. That's one of the tests you want to do. One test is to see what the loss is. One test is to stick a 50 ohm load on the end and look at the SWR looking down your coax. This is the third test. Look at the velocity factor of your coax. Or maybe you need to identify exactly what coax you have. This coax doesn't have any markings on it except that it's Beckman, made in USA. So the only way you can find out what it is by finding out what its velocity factor is, finding out what its loss is, looking at those, and then start perusing data sheets to find out who it best fits. Or maybe you're preparing to make some kind of coaxial phasing harness or tuning stub where electrical length is everything. You have to know the velocity factor in order to do that accurately. So what do you need to know to do the velocity factor? The physical length of your coax. That's it. So how do you do it? Now, I'll stop real quick here. Distance to fault told me what? Electrical length of my coax, right? It told me electrical length of my coax. So, you perform the instructions for distance to fault measurement, and if your antenna analyzer happens to ask for a velocity factor, just tell it 1. And if you tell it 1, then what it will give you is the electrical length of your coax. Simple, simple, simple. So once you know the electrical length from the distance to fault, you just do some simple math. You have the physical length, you measured it physically, you know how long it is. You know the electrical length, what was reported here. You divide the physical length by the electrical length, and you get the velocity factor. Done. Just so happens the velocity factor of this cable came out to about 0.643 as opposed to 6.66. See, now you are an expert.